Okay. Lecture 2. So our aim is to speed up through all the boring details for now, and go directly to how we do calculus on submanifolds. So we have these weird pieces of Euclidean space which look like a Euclidean subspace if you go really close, and we want to do calculus on them. Why? The main idea is what you already studied in any course on calculus on several real variables. So optimization problems on submanifolds, constraint optimization problems. To give you, the next lectures, in lecture 3, we will be analyzing the one of the algorithms for optimization on submanifolds, the easy version we can talk about now. And in lecture 4, we will be looking into at least one application. I mean, a concrete application, not an exercise. Why all these efforts to do calculus on submanifolds? I mean, if you could think, okay, we were doing it in calculus 2, we can do it now without knowing what a submanifold is. That's true, up to a point. Because many times the manifold structure helps you a lot in, not directly in doing computations, because if you are at the point where you are doing computations, it's too late. The help comes before. It comes when you have to devise the algorithm, to understand what's the better way to code something. To do that, we have to talk about all the stuff we need also in Rn to tackle any optimization problem. So we have to talk about the extremal points, we have to talk about maxima and minima and whatever. So we want to define at first the gradient of a scalar function. So we have a function from our k-dimension submanifold to R, for example, and we want to define the gradient of f. Okay, this is not... I mean, you could have in mind some definitions. You could think about some definitions. So let's do it systematically. We try to generalize partial directional derivatives. What does it mean? On Rn, it just means moving along a line and taking the derivative of this function, which is a function now from R to R. Problem, first problem, inside of a manifold, think a sphere or something like that, a torus or the orthogonal group, you don't have lines. You don't have straight lines. What do you have? You have curves. One-dimensional things are curves. So a curve, for us, is just a smooth map from some interval. We choose -1, 1, but it's just it could be -5, 3, whatever. Usually you want 0 to be in it just because you want to use 0 as a special point, but who cares? You could take an interval which is the interval from 10 to 11 and pick up as a special point 10.5. Weird, but allowed. But I mean, now you have a lot of stuff. I mean, straight lines, in R2, straight lines are those. I mean, you can parameterize easily straight lines through the origin. If you take a sphere and a point, curves through a point on the sphere are a lot. And it's not easy to work with them. So we could do something easier. And we just consider the tangent vectors to the curves. So, what do I mean? you have your manifold. Obviously, I'm drawing R3. And we pick up a point. And we start drawing curves through this point. So, I don't know. We have this one. You have this one. You have this one. I mean, you have a lot of curves that go through the point. I don't consider all the curves. I just consider their tangent vectors in the point. So for every gamma, I'm considering gamma dot at 0, with the idea that at 0 all the curves are in P. So these are the velocity vectors of your curves, and these are all applied in a way in P. So here you have your vectors, which are through P and are tangent to the curves. I know that the drawing is horrible, but I hope you understood. The tangent space is a collection of all the possible velocity vectors. So the tangent space at P of M is the set of the vectors obtained as the derivative of gamma in 0, where gamma to M is smooth, from minus 1, 1 to M is smooth, and gamma of 0 is equal to P. So, well, obviously this is called the tangent space at P because, well, it's all the curves go through P and we are taking the velocity at P. Why is the tangent space to M? Because all the curves lie on M. They don't go outside of M. Okay, so the tangent space. The tangent space of Rn is Rn. And the tangent space of any affine subspace is the same is true is not exactly true. So the tangent space of an affine subspace is not the affine subspace. It's the vector subspace which is parallel to it. But anyway, this is a bit of... By the local characterization of submanifolds, the tangent space at P of M is Rk for all P in M, if M is a k-dimensional submanifold. Why? Well, what happened? You have your submanifold. You have a small part and you have what is called a coordinate chart. So it's a map into Rk which sends this small piece of your manifold into an open set in Rk. What is happening? Well, if you have gamma from minus 1, 1 to M, quite easily you obtain phi composed gamma from minus 1 to Rk. And if you remember, I went through it quite fast, but phi, the coordinate chart, so this map is a diffeomorphism. So it has an inverse, which is again smooth. So you can come back. So not only every curve here goes to a curve here, but on the other hand, every curve here can be brought back to a curve on M. So you can identify the two sets of tangent vectors. This is not a proof, it's just an idea, but I hope you understand it. Well, this third one is maybe less trivial. Let's see if no. If you have a defining function, so a function that defines your set for which the M is 0 of this function and the Jacobian matrix is full rank, then the tangent space is the kernel of the Jacobian matrix. Again, well, okay, this comes exactly from the linearization property that we talked about in the last, in the previous lecture. So again, you have your manifold. If you remember, you not only can find a diffeomorphism from this small open set to an open set in Rk, but you can actually find a ball in Rn around it, and you can linearize things completely. So you can find in a fine subspace, a linear subspace, you can translate it, and an open, maybe not as nice as the previous one, but another open set that intersects your, this is a change of coordinates. That intersects your linear space in an open set which is diffeomorphic to the one you picked on the manifold, on the submanifold. But now, if you add a defining function here, so Rn minus k, f, you will have here another defining function, but this is just linear. And for a linear function, the zero set is just the kernel. And for an affine subspace or a linear subspace, the tangent space is the space itself. So if your space is already straight, linear, the tangent space is the space itself. Because the curves, I mean, every direction can be obtained just by the straight line going through that direction. So on this side, the tangent space is clearly Rk, so it has to be also on this side. Because this change of coordinates gives you a correspondence between the tangent space here and tangent space here. Again, if you have any questions, stop me. Now we can define the directional derivatives. Given a vector in the tangent space, because the tangent space here is always a vector space. Given a vector in tangent space at P, the directional derivative of f, we denote it for now as the f in the V at P, is just the derivative of f composed with gamma, where gamma is any curve that has that velocity vector. So if you have a tangent vector, so a vector of the tangent space, you take any curve that gives you that vector as a velocity. You compose you just look at your function along that curve and take the derivative. If you apply it with gamma in Rn, with gamma the constant speed parameterization of a straight line, you have the directional derivative in Rn. Now, we bring into a function. We fix a function and consider this map. For every v in the tangent space, we calculate the directional derivative of f at v. This is linear. You can again, it's again the same proof that I did before, with the local linearization and whatever. This map is linear in V. Once you fix f and p, obviously, you're fixing everything. Therefore, by Reed's theorem, which I hope you all know, but so if you have a vector space and you have both with a scalar product, so Rn with a scalar product, for example, and you have a linear function from V to R, then you can write L as the scalar product of V with a fixed vector VL. Okay, if you think about it in Rn, it's obvious. In Rn, L of x will be just given by L applied to the canonical basis as a row vector multiplied by x. So this is your VL transpose. And this is Reed's theorem, Reed's representation theorem. But anyway, it's a big name for something easy. So I formulated it for a vector space, generic vector space with a scalar product, because in general we will be using it in this fashion, but for now we are in Rn. So this is a linear functional, so we can find an element of the tangent space, which is an Euclidean subspace of Rn, so it's a space of Rn with an Euclidean structure, so with a scalar product. We can find an element such that the directional derivative of f along V is just a scalar product between this vector and V for every B. Again, we are fixing f and p, and you see here that this vector depends on f, on p, on m. This vector is the gradient of f along m in P. So it's This is also, I mean, you know it already in, you already know this formula in Rn problem. The directional derivatives are computed by taking the scalar product of the gradient with the vector. Here we are just going the other way. Now, for each P of M, you can consider the orthogonal projection from Rn, well, Rn to Rn, whose image is the tangent space. So the tangent space is an Euclidean subspace, so you can take the orthogonal projection. This is the important fact. The gradient along M of a function is the projection of the usual gradient in Rn of any extension of this function. So if you remember, you have M, you have a function f. What does it mean for f to be smooth? Well, it means that f can be locally extended to a smooth function all around M. So you have a some tube around M or something like that. Here you have your M inside. And you have a function f tilde, which is defined all around M, such that for the points in M, f tilde is equal to f. Now, you can extend the function in a lot of ways. F tilde can be defined in infinitely many ways. So the gradient of f tilde, even at the points of M, can be whatever you want, more or less. What's fixed? Well, if you project this gradient of any extension on the tangent space of M, you have the gradient of f. And again, the proof is the so here you have maybe your gradient of f tilde. You have the tangent space to M. And the orthogonal projection here is the gradient along M of f. So the red vector depends on the extension you take. And the extension, you can take it in many, many ways. The orange vector does not, as long as you take the orthogonal projection. You don't take any projection. It's the orthogonal projection in the tangent space. So we have this formula, which is actually very useful when you have to do computations. I mean, actual computation on a machine with code. The gradient along M is the orthogonal projection on the tangent space of any smooth extension of f. Now, external points. Well, maximum and minimum are defined in set theoretical way. So the maximum of f on M is a point such that the values of f at all the other points are less than or equal. So it's just, and the minimum is the other way around. As in Rn, you have the trichotomy, so you have the singular points where f is not differentiable. You have critical points where the gradient of f vanishes, and you have boundary points, maybe. We haven't talked about manifolds with boundary, but you can cut a manifold in submanifold of N with some inequality condition and you obtain a boundary. Critical points are where the gradient vanishes. Now, if you put everything together, if you have a local defining function, so a function such that M is the zero of this function and the Jacobian of the function, the Jacobian matrix of the function has maximal rank all around, the gradient along M being zero means that the gradient of any extension, I'm not writing F tilde, but when I don't put the M up is the gradient in Rn, so it's on any extension. The gradient of any extension is orthogonal to the tangent space. So think about it. We had the projection of the tangent space. Now we're saying, what does it mean that the gradient is zero? That the projection is zero, so the original gradient is orthogonal. So the gradient of any extension is orthogonal to the kernel of the differential, because we proved before that the tangent space is the kernel of the Jacobian matrix. So you are saying the gradient is orthogonal to the kernel of the Jacobian matrix. This is easy linear algebra. The kernel of a matrix is the image of the transpose, is orthogonal to the image of the transpose. So being orthogonal to the kernel means being inside the image of the transpose matrix. Now, exercise in real analysis, write down, and linear algebra, half and half, write down this condition, and you will see that this is exactly the condition of the Lagrange multipliers. In case of n constraints, obviously. So what does it mean for the gradient to be in the image of the transpose of the matrix? It means to be linear combination of the rows of the matrix, and the coefficients of the linear combination are the multipliers of the Lagrange multiplier system. So this picture fits in the Lagrange multiplier picture, and it is exactly the same thing. Just we have found an intrinsic way to talk about this. Now, to a more abstract part, the tangent bundle. You can glue together all the tangent spaces. So for every point on your manifold, you have a tangent space. Think about the sphere. Well, no, think about the circle. This is a one-dimensional embedded submanifold in R2. For every point, you have a tangent space. This goes on. I'm drawing them attached to the point on the circle because it's easier to picture them in your mind like this, but they are actually vector subspaces of R2, so they should all be passing through the origin. Actually, the point where they touch the circle is their origin. So for any point, you have your tangent space. And even if drawing them, they intersect, in reality they do not, because the tangent space at this point and the tangent space at this other point don't have anything in common. So it's just that the drawing is not good enough to picture them, but they are all separate lines. Okay? So in fact, the tangent bundle, the collection of all tangent subspaces, the tangent spaces, is not for the circle inside R2. I mean, not naturally. This is tangent bundle. So the tangent bundle is the set of the couples point vector in Rn times Rn. So for the circle would be in R2 times R2, so in 4 dimensions, in 4-dimensional ambient space. So that P is in M and the vector is tangent to M. and you have a map that projects Tm on the first component, so projects Tm on M. What are the preimages of this function? The preimages of these functions are the tangent spaces. So pi to the minus 1 of a point in M is the tangent space at that point to M. You can show that this is again, well, you can show, or maybe I've written, yes. If you remember, okay, if you take a defining function for M, the tangent space is the kernel of the Jacobian matrix. So it's just as easy as this. The defining function for the tangent bundle is the defining function for the manifold and the Jacobian matrix. When both are 0, you have a point x which belongs to M and a vector y which belongs to the tangent space at x. And it's easy to work out the details. This is a 2k dimensional submanifold in R2n. So the tangent space to the circle is a surface. Because the circle has dimension 1, the tangent bundle has dimension 2. Why is it called bundle? Because you bundle together, you collect together all the tangent spaces. Now, you can show that the tangent bundle of S1 of the circle is diffeomorphic to R2 minus the origin. Not in the way I pictured it, but you can find a diffeomorphism from R2 minus the origin to the tangent bundle of the circle. Exercise. And this is just a more difficult. The tangent bundle to S2 is diffeomorphic to the zero locus in C4. Yes. No. Should be C3. Yes, sorry. There is one variable. Now, this is tangent bundle to the tree sphere in R4. So you either put a tree here or erase one coordinate here and put it in C3, well, whatever you want. Sorry. You have other bundles, for example, the normal bundle. You can play with vector spaces now. Instead of considering all the points and the tangent vectors, you take all the points and the vectors orthogonal to the tangent space. You have a natural projection, and I think you could write down the defining function. Point by point, the normal space is the orthogonal to the tangent space. So, for example, and now we can picture it. Well, think of this as a circle. It's not really a circle, but whatever. For any point, you can easily draw the normal space. It's again one-dimensional. This picture holds in any dimension, because if this, instead of the circle, you think about the sphere in any dimension, the normal space is just the radius through that point. I mean, it is diffeomorphic to the half line through that point. So you stop at the origin. You don't include the origin. Anyway, it's not important. Now, the normal bundle of S1 is diffeomorphic to the tangent bundle of S1. This is what I was saying before. And we, well, normal bundle is not that important. We pass to another, this one is important. Okay, submersion means that the wait. Okay, well, erase the first sentence. If E is either the tangent to the normal bundle and pi is the projection. If you have an open set in M, then a section of the projection is a function from the open set to E, such that the projection of sigma is P for every P. So this is called the section because you usually think about it in this way. You have an open set and you have something bigger, like of a higher dimension, which projects down. And for every point, for example, you have a line, you have a vector space, something like that, no? This is pi minus 1 of P. What is a section? A section is a map from here to here, sigma, which chooses for every point of the base, chooses one per image. And so you end up with something like that, which for every point meets the per image exactly in one point. So this is sigma of P, this is sigma of Q, okay? And it's called the section because it cuts the big space above. A tangent vector field is for every point the choice of a vector. A field of tangent vectors is for every point of the manifold the choice of a tangent vector. So it's a section of the tangent bundle. So for every point you pick a tangent vector. A normal vector field is that for every point you pick a normal vector. Usually we are interested in sections with some regularity condition, for example smooth, continuous, whatever. And this is just a fun thing that it's not important, but I mean the name is worth it, the Hairy-Ball theorem. You cannot count the Hairy-Ball. So if you cannot find a non-vanishing tangent vector field on the sphere. If for every point of the sphere continuous, if for every point of the sphere you pick a tangent vector in a continuous way, at some point it doesn't work. You have to put something to zero. You cannot have a non-zero tangent vector at every point of the two sphere. And this is called the Hairy-Ball theorem. So any continuous tangent vector field on S2 must vanish somewhere. That's the bottom line. Now, the gradient vector field, just to sum up everything, we defined a gradient at each point. So we extend the function, we compute the gradient of the function in the ambient space, and we project the gradient. That's a recipe for our gradient vector at every point. So we can glue those up. The problem would be to show that this is a section, so it's a vector field, so it's a smooth map from the manifold to its tangent bundle. You can do it step by step. You extend it to Rn. The gradient, the usual gradient in Rn is smooth, because if f is a infinity function, its gradient is a smooth function from an open set to Rn. Now this is a bit tricky, I won't prove it, it's not difficult, but the map that gives for every point P, the matrix of the orthogonal projection in the tangent space is smooth from your submanifold to the space of matrices. GL and R is the space of, is the linear group of Rn. So this is a smooth map. Entry by entry of your projection matrix, this is smooth. Therefore, P goes to the projection on the tangent space of P of the gradient of the extension is a smooth map from M to the tangent boundary, because we are composing smooth maps. This is the gradient along M, and this means that the gradient along M of F is the smooth section of the tangent bundle, so it's a tangent vector field. So it's what we call the tangent vector field. Is giving to every point of M a tangent vector in a smooth way. Now, yes, quickly, the last part. We have almost we have everything to talk about critical points. Usually, at some point, you study critical points also by studying the Hessian of the function. I want to show you now in the last few minutes that the Hessian is a very difficult concept on a submanifold. So the gradient was not that, I mean, it was intuitive, no? You have the gradient of your extension, you project it down in tangent space, it works. Now, the differential of a smooth map. You have two submanifolds, M and N, in R M and R N, and you have a smooth map from M to N. So it's a map that extends to a smooth map of the ambient to the ambient. If you take a curve in M, the composition gives you a curve in N. So what I mean is that you have your manifold here, you have F, and you have another manifold here. You take a curve, so which is a map from some interval to your M. If you compose via F, you obtain another map from the same interval to M. This is M, and this is N. So curves in M go to curves in N. M and N was not a good choice, but anyway. This means that we can find some consequence on the tangent space. And that's what we do. The differential of a smooth map is the linear map induced on the tangent space. If F picks a curve in M and brings it to a curve in N, it means that it defines a map from the tangent spaces of M to the tangent spaces of N. And this is a linear map. So this is the definition. If eta is the composition of F with gamma, the image of this velocity of gamma is the velocity of eta. This is well defined. You have to check a bit of, the well-posedness of the definition, whatever, but it works. df, so as a function of the point and the vector, is a smooth map from the tangent bundle to the tangent bundle. So what I'm stressing here is that all the constructions work on multiple levels. So you have a manifold and you have the tangent spaces. The collection of the tangent spaces is again a manifold. You have smooth maps induce maps, linear maps on the tangent spaces. But the collection of all these smooth maps, these linear maps, is again a smooth map between the bundles. So once you can do something for your manifold, you can do something for a lot of other objects, which you have obtained like that. Now, this slide had to be before the other one, but anyway, if the differential at a point is an injective linear map, you talk about an immersion. If the differential at a given point is surjective, you talk about submersion. And the map is a diffeomorphism if and only if it's bijective and its differential is invertible at all points, meaning it's an immersion and a submersion. Now, the complicated thing, which is the last thing I want you to show, because it's why the Hessian is so, I mean, it's not easy. Take your map f from M to R. Take the gradient, which is a smooth map from M to the tangent boundary. You can take the differential of the gradient. So the gradient is a smooth map from the manifold to the tangent boundary. As a smooth map, you take the differential of this one. And this differential has rank k at every point, because the second component is p goes to the gradient, but the first component is p goes to p, because the tangent bundle is the set of couples p and tangent vector to p. Your map sends p to p, comma, the gradient of f. So in the first component, it's just identity. So its differential is a map from, well, one tangent space to the other bigger tangent space. The second tangent space is decomposed in two tangent spaces. And on the first part, on the first coordinates, your differential is just the identity k by k. So we just look at the second part. The projection of differential on the gradient on the tangent space, this tangent space here, which is a factor of the tangent space of tangent boundary. So the differential of the gradient acts as the identity on the first factor, and he has a second component which we denote, well, I denote it by this notation. Oops. So this is the Hessian, which is a bit complicated, but or at least that is a linear map. The Hessian is a bilinear map. How do you obtain the Hessian? Taking the scalar product between the linear map applied to a vector and another vector. It turns out to be symmetric, and it's called the Hessian of f on M. Now, the last thing. You could compare the Hessian of f to the Hessian of an extension. It doesn't work as before. It's not just the projection. There is a difference between the two. And the difference between the two is how much the manifold curves. The difference between the two is a linear function of the gradient, and as a linear function is a bilinear map from the tangent space times the tangent space to the normal space. Okay, it's a bit complicated, but I don't want to really explain this. I just want to show you that as soon as you move on from the gradient, things get awfully complicated. So the Hessian is difficult to compute because it's not just the restriction, it's not just the projection, it's the restriction of the global Hessian plus another term, which is the second fundamental form, or is also called the shape operator. And it's linked to how much your manifold curves and varies. The main idea is that the gradient is the velocity of the curves. The Hessian has to do with the acceleration of the curves. And if you compute the second derivative of the composition, you have two terms. It's a sum of two terms. I really don't want to go into this. We will talk about this with the right formalism in a couple of weeks, probably. So that's why we won't be talking about the Hessian at first. And this is it about the calculus of submanifolds.